So, as Fernando mentioned during his talk, if calendars or similar applications break, it can really cause a lot of trouble for users. And the friction between usability and privacy is really one of the main concerns when deploying end-to-end encryption at scale. So in our next talk, we're going to have Gordon, who's a security engineer at Google, tell us a little bit about some of these frictions that can arise and challenges with usability in large-scale deployments of end-to-end encrypted cloud storage.
Thank you. Okay, thanks. Hi, everyone. My name's Gordon. Today we're going to be talking about some difficulties that we encountered when we tried to use the provable security models for end-to-end encrypted cloud storage in the literature to look at the end-to-end encryption offerings that we do in Google. As we'll see later in the talk, most of these difficulties stem from functionality introduced to mitigate data loss both in typical and disaster recovery scenarios. This talk is joint work with my colleague Fernando, also at Google. So for those that don't know, although most people probably do, in the end-to-end encrypted cloud storage setting or just secure cloud storage, a user wants to outsource the storage of their data to a cloud provider, but they don't want the cloud provider to see the underlying data or be able to tamper with it. This was only kind of semi-recently formalized by Beckendahl, Davis, Gunther, Haller, and Patterson in 2024. This is the paper that Fernando just talked about that gave also a specific scheme called CSS. And the way it works is basically you have a bunch of two-party protocols between the user's clients and the cloud provider that will allow you to upload, access, modify, and even share files across users. And the security of this is kind of hinged on a master password, which is sampled from some distribution. Security is defined in terms of two things. Confidentiality is a left to right indistinguishability game in the game-based setting, and integrity is a forgery game as well. Now, this functionality seems kind of simple, but it's actually able to capture a lot of rich use cases at Google. So Google Maps offers an end-to-end encryption setting for your location history, your passwords and passkeys in Google Password Manager, and also Android backup and restore can all be represented in this setting. Now, it might make sense to think a little bit about how end-to-end encryption works from a Google developer's perspective and how we do it to see how to apply this model. Because we have a bunch of different first-party products, we want to provide very common infrastructure for our developers, whether that YouTube, Gmail, or Drive, to implement end-to-end encryption. And so we have this library that we provide that they can just import, and when a user first wants to enroll and do end-to-end encryption, they're going to generate a key, and then later they're going to kind of enroll this key with what we call a knowledge factor. So the knowledge factor you can think of as morally equivalent to the master password in the Beckendahl scheme. And then there's some protocol, of course, to kind of securely get this wrapped key with the knowledge factor onto the server. Then later, when we want to use this key either on the same device or a different device that doesn't have the key, the user is just going to input their knowledge factor, interact with the cloud provider, and get the key back. So far, if you squint, you can analyze this using the Beckendahl et al. Model, right? The user's knowledge factor is just the master password, and then the end-to-end encryption key is just an implementation detail of a concrete protocol that you would prove secure in the framework. But things get a little bit more complex as you go on. So the first thing is that we don't just have one knowledge factor. Users can have different types of knowledge factors. Generally speaking, there's kind of two broad categories. So the first one you could think of as like a low entropy portable or memorable factor. This is maybe like a PIN or a password. And in contrast, you can also think of very high entropy factors. So, YubiKeys are the security keys. They support like a PRF extension in FIDO and web authentication. So this is actually like a cryptographically strong key. And so, oops, sorry, I advanced the slides a bit too fast. Yes, here. And the key thing here is that these knowledge factors, they use different mechanisms to secure the end-to-end encryption key, right? So for the PRF case, you can imagine just deriving a wrapping key directly from the PRF and then wrapping the end-to-end encryption key. But in the low entropy setting, if you just did that naively, then you kind of need brute force protections because those are not secure. So the key part here is this is still not disqualifying from using the Beckendahl et al. Model, right? You just have to, basically you have a bunch of individual proofs for each knowledge factor that says like, okay, if the master password is this type of knowledge factor, then the scheme is secure and life is fine. But the problem actually comes here is that the same users might actually use multiple types of knowledge factors to encrypt the same end-to-end encryption key. And this is mostly to prevent data loss in kind of the typical scenario. So assume that Alice has already kind of enrolled an end-to-end encryption key with her her portable low memory knowledge factor, maybe the PIN. If she wants to recover it or recover the key on a new device, she'll just put that PIN in on that device and get the key back. Now the problem here that we want to avoid is that Alice might forget her end-to-end encryption PIN. Maybe she set it in 2022. It's now 2026. She wants to get her data back, and this is not her account password, so she just doesn't remember it. To kind of hedge off this case, what we do is we're going to opportunistically enroll a device-specific knowledge factor every time that Alice uses a portable factor. So she's going to use a PIN on her new device. We're then going to create a virtual PRF key on that device, and then kind of enroll that same end-to-end encryption key using that knowledge factor. And so now the problem is kind of obvious, right? The same user for the same end-to-end encryption key might use different knowledge factors to protect that and safeguard it. And so in this case, even if you had individual proofs that, that for this type of knowledge factor, this scheme is secure in the Beck-and-Dall et al. Model, because the Beck-and-Dall et al. Model is a game-based, it's not clear how these things compose. So it could be that, individually each piece is secure, but the composition doesn't give you that. So that's one thing that we're kind of missing from the literature. The other wrinkle is, whereas we just talked about avoiding typical kind of data loss where you forget your portable PIN but you still have access to your device, users care about a disaster recovery. So this is a quite drastic scenario. It's not only have you forgotten all your knowledge factors like your PINs, but you also have lost access to your device. Maybe it was stolen, or a factory reset or something like that. And users actually want to be able to recover their data, even in this case. Now, naturally, this feels like there's some possibility here. Clearly, if there is a two-party protocol in which a know-nothing client and on a server can recover the end user's key, well, then presumably a malicious server could just simulate that protocol and then get the victim's key. So it seems like this is at odds with the security definition. The good news is whenever there's a two-party impossibility result, we can just introduce a third party and life is fine. So this is, I think, what Google and Apple both do. They do something called recovery contacts, which you can think of as someone who's a friend, a partner, or someone in your community that you trust, and they will help you kind of bootstrap recovery when you've truly lost everything. This is a sketch of how it works. Google and Apple do it a bit differently, but it's at least generalized. So during the happy path, while you have your end-to-end encryption key, you just secret share. You give one share to the cloud provider, one share to your recovery contact, and then later, when you are in a disaster scenario, if you can somehow out of band convince the cloud provider or your recovery contact of who you are, they'll give you back the shares and you can recover the key. Now, this is kind of what industry does, but it is currently not in the end-to-end encrypted cloud storage models. They're all kind of two-party protocols. So here's the third party. And not only in terms of interfaces does this raise a question, but there's also questions of what should the security be, right? The way this is designed, like the recovery contact doesn't see the end user's end-to-end encryption key, which is probably a good feature. But if you just use a naive secret sharing scheme, right, the cloud provider could influence what key is actually recovered, and that could eventually lead to an attack on integrity as well. So we need some kind of more rigorous formal definitions, both at an interface level and at a threat modeling level that are missing. Cool. So in short, let me look at my time. We blasted through that one. So in short, the way that we kind of implement end-to-end encryption in industry, at least for the cloud storage setting, there are some kind of complexities here that make it hard to apply the current state-of-the-art models for provable security in the cloud storage setting. In particular, we don't just have one master password. We have the same user can use multiple knowledge factors to encrypt the same end-to-end encryption key, and that poses a problem for composability that we need to address. And lastly, users really expect to recover their data. There is a specific subset of people for where you can say, we're going to offer the strongest variant of end-to-end encryption possible. And in that case, you can't recover your data. And that might work for some people, especially in the cases that we talked about in the earlier session. But for the vast majority of users who we just kind of want to make end-to-end encryption more universal for, data loss is a very big problem. And that's kind of, it's also not really well understood. And so the hope here is that if we can address that, then we can kind of make end-to-end encryption used a bit more. And so here, in the specific case, we just need not only we just need kind of more interfaces and definitions in the literature that we can actually use, as opposed to industry kind of going on the bleeding edge and figuring things out. And so hopefully this talk, I think most of the people that were co-authored on that paper are in the room. So hopefully this spurs ideas for future research in this direction. Thank you.
Indeed, it surely will. Thank you so much for giving this very nice overview of the open challenges. We'll take some questions while we transition to the slides of the next speaker. So are there any questions in the room? If not, I'm sort of curious, how far did you get in your work on provable security? We chatted a little bit about this, but maybe you want to tell the room, like, where are you at? Did you do any proofs for the existing schemes, or are you looking into defining these things yourselves? Or
Makes sense. Yes, we did some work on the PRF knowledge factor is the easiest one to prove because it's you just assume that there's a high entropy cryptographic secret, and then you can kind of wrap the key and do that. So we have some work on proving the PRF knowledge factor. We've not done any work on doing the low entropy ones. I think WhatsApp has a paper on encrypted backups that they've done.
some of the authors
that
are also here
earlier.
today. Yeah.
So that's kind of where the state is right now. I think our hope is that eventually we do want to get everything to be provably secure, but this effort kind of is just started maybe a year ago or so.
Great. Let's thank Gordon again.